The very first topic is abelian group, which is 9.1. As we can see the definition and the laws on the screen, what it says, an abelian group G with steric is a set G with a binary operation. What is binary operation? We'll study further later. Such that it satisfies closure law. That's mean any relation we'll apply, it belongs to the group G. Next is associative law, which is this. These elements belongs to the group G, and if we'll separate our brackets or parentheses, uh, we should get equal answer. Next is identity law. There exists an element E belongs to the group for which if we'll subtract, multiply or any operation which is given to us, we'll get our same element which belongs to the group G. Next one is inverse law. For all x belongs to G, if there exists an element y belongs to G such that if I multiply or add or any operation which is given to us, I'll get the identity. And both the elements belongs to the group. Next one is commutative law, which is if I reciprocate to each other, not reciprocate, if I change the position of the two elements, I should get the same answer of both the operations via both the sides. So these members should also belong to the group G. These are called the axioms for abelian group. They are not the axioms in the sense that that's often used in Euclidean geometry. If a system satisfies all five properties, then it qualifies in an abelian group. As we have studied binary operation in these last 5 laws, so what is binary operation? Binary operation on G is simply a function f, G cross G, which I'll get the member from the G, that is a function of two variables in G that assigns to every pair of elements A, B belongs to the group. An element, that function also belongs to a group, but it's more usual to write the name of the function between the two variables. So instead of writing steric A, B, we write a steric B. In other words, we are talking about a algebraic system with sort of abstract addition or multiplication where we combine any two elements. So let's begin with example number 1. The most obvious example of the abelian groups are the system of numbers where addition is just ordinary addition. Real numbers with addition is the abelian groups. Rational numbers also form abelian group. Integers, with ordinary addition is also an abelian group, and even integer is also an abelian group. Now the next example is set of numbers can be abelian group under multiplication, but we need to leave out 0 because 0 doesn't have an inverse under multiplication. For example, real numbers with non-zero real numbers under multiplication forms abelian group, and rational number with non-zero under multiplication forms abelian group. Now we'll do some examples which don't qualify for an abelian groups. So here's the example number 3. System which don't qualify as abelian groups are the set of prime numbers under addition. This isn't an abelian group because it doesn't satisfy the closure law. The sum of two positive prime number isn't always a prime number. The set of real numbers under subtraction. This isn't an abelian group because subtraction isn't associative. If it were, we'd have to, if we apply associativity on the subtraction of the real numbers, we can't get equality. Now the next example is the set of 2 by 2 invertible real matrices under matrix multiplication. This is a group, but not an abelian one because the commutative law doesn't hold. Next one is the set of all positive real numbers under addition. This isn't an abelian group because there's no identity 0. The identity for addition isn't in this set on which positive real numbers. Now the next one is the set of all integers under multiplication. This isn't an abelian group because it doesn't contain inverses for all its elements. Negative half isn't an integer. All of the examples given so far it's have been infinite, and now we'll do some finite examples. As you can see on your screen, the binary operation under under the set A B C D, which is an abelian group. As we can see here, closure is obvious. The associative law is somewhat, we can check it. We'll get the associativity is will be fulfilled in this group, and the commutativity is also obvious. The identity is, if I'll check my identity by, if I multiply A by A, I'll get C, B by B, I'll get C. If I operate with C by C, I'll get C, D by D with C. So its identity element is C. So if I check in the diagonally, C appears. So the inverse law holds for this. The last example is on the screen, which is mod 4. As we can see, the table is on the screen. It has the same pattern as I discussed in the last example. Its identity element is 0. And so its inverse is also exists. Now let's move towards the next topic, which is isomorphic groups.